Hello everyone, my name is Liz Brannon and I'm a PhD student in the Mosman-Valtier lab at the University of Rhode Island. Today I'm going to take you on a trip to the Fields Point wastewater treatment plant where I conduct my thesis research. I'm currently looking at the greenhouse gas emissions from the biological nitrogen removal tanks at this plant. But before I get into too much detail, let me give you a little more background on why my research is so important. So you may be wondering, what is biological nitrogen removal? Why do we need it? And why am I measuring greenhouse gas emissions from it? The story starts a few years ago in Narragansett Bay. People were beginning to notice that the health of the bay was declining. More algae growth and low oxygen zones were being observed. It was determined that many of these symptoms were a result of excess nitrogen in the bay. This is known as eutrophication. It was also determined that wastewater treatment plants were responsible for 62 to 73% of the nitrogen load into the bay. This led Rhode Island to pass legislation in 2004 that required wastewater treatment plants to reduce their nitrogen loads to the bay by 50%. This is where biological nitrogen removal enters our story. In order to meet these new regulations, the Fields Point wastewater treatment plant upgraded existing tanks to perform biological nitrogen removal. These tanks remove nitrogen using bacteria and natural processes. Let's head to the plant and take a closer look at how this works.
All of the water coming in underneath this grating right here that everyone is walking on top of, and it is flowing into this tank here underneath the surface, so you can't see that. What you're seeing coming in is return flow from the final clarifiers. That is going to flow this way into the pre-anoxic zone, which is this first strip here. And what is occurring in this tank, since there's low oxygen, we have nitrate being converted to N2O or N2 gas, hopefully N2 gas because that's inert. Then the water's going to flow over this waterfall into the IFAS aerated zone. IFAS stands for Integrated Fixed Film Activated Sludge. And it's called that because you can kind of probably see some black plastic media bubbling around in there, and that's giving the bacteria another surface and biofilm to grow on. What's happening in this zone, since we have oxygen, we have nitrification, which is converting the ammonium to nitrate. The water is then going to flow into the next zone. This is the post-anoxic zone. So we're back to low oxygen. So we're going to take that nitrate that was created in the previous tank and convert that to N2 gas. And then there's a final re-aeration zone, and this is just to help put some oxygen back into the water before it flows through the rest of the wastewater treatment plant and then eventually into the bay.
Okay, so the nitrogen is being removed, and now Narragansett Bay is healthy and all is well, right? Not quite. There may be an unintended consequence in this nitrogen removal process. Previous studies have shown that similar biological nitrogen removal processes have released greenhouse gas emissions, including carbon dioxide, methane, and nitrous oxide. Wait, hold on a second. What is a greenhouse gas? Incoming solar radiation is absorbed by Earth's surface and converted to infrared radiation, which is emitted from Earth's surface. Greenhouse gases trap some of this infrared radiation in the atmosphere and help keep Earth at a livable temperature. However, if the concentration of greenhouse gases in the atmosphere continues to increase, more heat will be trapped and excess warming will occur, leading to climate change. Carbon dioxide, methane, and nitrous oxide are three of the most potent greenhouse gases in the atmosphere. Therefore, my research examines just how high emissions are from biological nitrogen removal. By decreasing the amount of nitrogen entering the bay, are we then in turn increasing the impact of wastewater treatment plants on climate change? Are we solving one problem but creating another? That is what I hope my research can help us figure out. Let's head back to the wastewater treatment plant and take a look at how I collect data on greenhouse gas emissions.
Alright, so now we're going to deploy the chamber in the IFAS aeration zone. You can tell it's aerated because we have some really obvious bubbles coming out of the top of it. And here we have our tubing. We have both an in and an out, and it's going to be running to our greenhouse gas analyzer. And now I'm just going to check with Dave. Actually, first here I'm going to do some untangling. Alrighty, now I'm going to check with Dave and make sure he is ready to go on the other side of the tank. And he is ready. Now we're going to move the chamber out until about as close as we can get to the middle of the tank. And right there looks good. And we will set it down. Now we're creating a gas-tight seal between the surface of the tank and the chamber. And the pump is pulling the air up out of the chamber through our end tubing into the analyzer. It's going to read the greenhouse gases and then send it back into the chamber through the output tubing. And we're now going to leave the chamber on here for about 5 to 8 minutes. And then we'll remove the chamber. All right, give Dave the okay. And now we're going to bring the chamber back to me. And now we'll take a look at the data, see what we got, see if we need to redo the chamber or move on to the next section of this zone.
After we finish all of the measurements for the day, we pack up and head back to the lab to take a look at the data. Here's an example of data from one chamber deployment. On the x-axis, we have the time in seconds that the chamber has been on the water. On the y-axis is the concentration of nitrous oxide in parts per million from the analyzer. As you can see, the concentration of nitrous oxide in the chamber is increasing over time. This indicates that nitrous oxide is being emitted from the surface of the tank. The final step is to convert the change in concentration over time in this graph into a flux. A flux is the rate at which a physical property, in our case, greenhouse gas, flows through a given area. The flux of each gas from each chamber is calculated using the ideal gas law and Fick's law. After a year of data collection, preliminary results indicate that nitrous oxide, carbon dioxide, and methane fluxes from the tanks vary by over an order of magnitude throughout the course of the year. The largest nitrous oxide fluxes can represent up to 1% of the nitrogen removed from the water. The good news is that the nitrogen removal has been working. Since the tanks came online, the plant has been able to meet the new requirements. It seems that fluxes can be significant on certain days, and my future research will begin to examine what causes these larger emissions. I hope to continue working with the staff at the plant to make the process as efficient as possible.